Okay, our today's laboratory work is dedicated to band structure calculations with quantum espresso. But at the beginning, I want to tell you about what is band structure. I think you all know what is it from at least Alexander Korduk's lectures, and maybe before Carl, you also knew what is it, but I will remind you. The books I will send you today, Solids and Surfaces and Electronic Structure of Materials, they are really good books to read about this issue. And in this laboratory work and in the next laboratory works, I will use some things, some screens, some pictures from these two books, because they, as I think they are brilliant. So Roald Hoffmann is a Nobel Prize winner. He was born in Zolochiv. Today it's Lviv Oblast in Ukraine. And in 1937, that time it was Poland. And then he and his family, they moved away from Soviet Union because they scared for their life. So they moved to Canada, and he made his career in Canada. And he, in 1981, he got a Nobel Prize in chemistry. So he got it for his work with explaining connections inside solid bodies. And his work, his book Solids and Surfaces is dedicated to this theme, to bonding inside some crystals. And you see he is in the photo with some model of crystal. And he also gave some, as I know, he also gave some interviews to Ukrainian medias in last years because of his Ukrainian connection to Zolochiv. So it's our so it's Nobel Prize winner who was born in Ukraine. And Electronic Structure of Materials, Adrian Sata is also good book. So if solids and surfaces, it's like chemist view. So it calls it chemist view of bonding. You will not find here a lot of mathematics. You will find here a lot of pictures, a lot of some bonds, connections, and some other things. But Electronic Structure of Materials is a book for physicists from physics, and he have wrote this book with a lot of formulas, but they are also useful. So I will start. It's from Solids and Surfaces. And I will start explaining what is band structure from infinite chain of atoms. Let's assume that we have this chain of atoms 0, 1, 2, 3, and so on to infinite. And to each atom, for each atom, we know some state. He0, he1, he2, and so on. Distance between these atoms will be a. So just very simple case. And what psi function, what wave function will be for this system? We just should summarize all these wave functions for each this atom as a plane wave. So he is a state, he n some n's state, and the exponent e k n a. It's some it shows that we work with plane waves. E is imaginary 1 and k and a. And for k equals 0, k equals 0, it's the center of our Brillouin zone. What picture we will have? We will have very simple picture. So all exponents will go to 1. So it will be just he0 plus he1 plus he2 and so on. But if we will use another k, not in the center of Brillouin zone, but on the border of Brillouin zone, k equals p divided by a, we'll have another picture. all these exponents, they will create -1 in the power of n. So it will be like plus, minus, and so on. -1 in the power of 1 will be 1, -1, then it will be 1, -1, and so on. And we'll have, and this state we will call antibonding. So first state we will call bonding, because we have all the states just summarized, but another state with some states so I take plus some states and minus some states, we call it antibonding state. So in the center of our Brillouin zone, the energy will be the lowest, and on the border of Brillouin zone we'll have higher energy, because here we have this anti-bonding state. And the picture will look like this. In the center we have all these circles. The same, it will be bonding state, center of our simple Brillouin zone. This is the most simple Brillouin zone. It will correspond to gamma point in a 3D Brillouin zone. P divided by A minus P divided by A are borders on this Brillouin zone, and we have here our anti-bonding states. You see, blue, white, and so on. And energy here will be higher than energy in the center of Brillouin zone, and we have some parabola. But we don't know what will happen. We can say what will happen in next Brillouin zones. We will have the same picture. It will be also parabolas from here and here, and we can even calculate the energy. So the energy, it will be the energy of free particle. So just Planck's constant K in the power of 2 divided by 2m. Kinetic energy. It's very simple. It's just parabola. What will happen if we will work, if we will change this A parameter? So if I will make rather huge parameter, 3 angstrom, for example, 3 angstroms. 3 angstroms is diamond silicon has 4 angstrom this lattice vector for its unit cell. So 3 angstroms is rather a huge distance, and we'll have this rather flat bond. You see, energy difference between border of Brillouin zone and center of Brillouin zone is not so huge. So we call this band flat or close to flat band. It's function of distance, yes. So if you will take huge distance, so we'll have just flat band, because energy difference will be very low. But if we will, because wave functions, they need space. If we will have very little space, we'll have huge wave functions here, huge oscillations. It's just from Heisenberg principle. Delta P impulse on delta X will be Planck constant. So if we will decrease this distance, we will have huge energy difference. A equals 2. It's for some model system. Of course, it's for some model system. We will see rather good parabola, but for A equals 1, we'll see this huge energy difference, this huge band. So this band is flat. You just see, then when we will see some flat bands on band structure of some material, you can see, yeah, okay, so this band is flat, so maybe some distance between atoms not so huge in this it's rather huge for these atoms. And if you see such crazy band, you know that something happens there. for example, atoms are very close to each other. Okay, and what will happen if I will what will happen if I will change this? If I will change this A, for example, I will take this and this atom closer to each other, and this atom will be on a higher distance. I can maybe it will be farther, yeah. So these two atoms will be closer. This will be far from this. These two also will be closer, and in this way, thus we will have this energy gap. So this energy gap occurs when we distort this chain, this ideal chain of atoms. So we'll get this energy gap with this plus minus delta E, which we'll get from this distortion. For more complex system, for surface, it's simple surface, but it's not so easy as a chain of atoms. Here we have atoms. Distance between these atoms A1 and A2. I think that the distance is equal in this example. And what Brillouin zone will have for this surface? Brillouin zone for chain of atoms is just line. It's just this line. It's very simple. It's 1D. We have this this parabola, and we have this Brillouin zone. But for surface, we'll have square Brillouin zone here. And center of Brillouin zone I will call gamma. Then points in the middle of these lines, of the sides, I will call X, and point in the corner I will call M. And then you will see that for even for 3D crystals, we use the same names. We use gamma is center of Brillouin zone. X is will be the center of some planes, and M always will be some corner points. And we have another situation. In gamma point, we have 0, 0. It's key X and key Y, K space. So in gamma we have 0, 0. Yes. Gamma is always the middle of Brillouin zone. And here it's just 0, and here it is 0, 0 because we have square Brillouin zone. 0, 0. X, if we will go here by this vector, it will be P divided by A. So it's the border of Brillouin zone by this vector, B2, and 0. P goes, and the same will be X here. So P divided by A, 0, 0, P divided by A. And M point is just two borders, P divided by A, P divided A. As and for each of these points, we will have another energy picture. You have 3 different energy pictures for this for this dose. If I will use the same circles, so this dashed circles will be plus. It represents lower energy state, and this white circle represents higher energy state, minus. So bonding and anti-bonding. So for center of Brillouin zone, we have all dashed states. So we have all states with low energy, and that's why for this simple case, gamma point also will be the minimum of energy. Then in the borders, in X points, we'll have this picture. So by X we'll have we have dashed and white then dashed and white. And for X here, we have this situation. So they're the same. And this energy will be higher than this energy because we have some number of this white. We have some number of this white states. And also we have some more combinations. For example, here and here. So all these combinations will be higher in energy than this energy. And for M point, we have this thing. So here you can see some structure. You can see that low energy states will be here, higher energy states will be here. So we can say that this energy will be lower than this energy, where all the states are mixed. They are totally mixed here. They're not random, but they are more mixed than here or here or here. That's why energy in X points will be higher than in gamma point and will be lower than in M point because we have this mixing. And we'll have this band structure, gamma point with the lowest energy here, then X point higher energy than gamma because we have this mixing, but we have the stripes with low energy states with higher energy states. This, and this. So our energy goes up. Then M point have more mixed states. That's why we have even higher energy. And from X point, we go to M, to the highest. M is the highest energy. And then we are going to gamma, from X to gamma, from M to gamma, and we have this huge energy difference. So it's how we can read these band structures in terms of energy. So if we have point with low energy, we can say that states are not so mixed. So we have the same low energy states, or they are not really mixed like in X, but they are highly mixed in M point. That's why we have here high energy, and then we can go here. So we can build rather simple band structure for this. I don't like this thing. I hope nothing will happen. Nothing bad will happen. Okay. We can draw such a simple band structure for this set of atoms. We have this band structure. And we used, as you see, we used only parabolas. We just took parabola here, then we took parabola here and parabola here. But we have a rather interesting picture. Then we are moving to 3D Brillouin zone, and it will be much harder than for 2D, because in 2D we have only 2 dimensions. 2 dimension, it will be like square on maybe some hexagonal. But here we have a lot of possible figures to represent Brillouin zone. For example, here is a Brillouin zone for cubic crystal, FCC crystal, and we have worked with this crystal in previous works. We can calculate these vectors in this way. And today I will show you how to work with these points, with these Brillouin zones, how to choose the path in this Brillouin zone to make our calculations. And we can start. So it was just short overview of what is band structure, and now we will calculate this band structure by ourselves. band structure is allowed energies of electrons in the structure. So here by dashed circles was represented low energy states, for example, electron in the lower orbital, and here will be higher. White is higher energy state, so it's electron on higher orbital. And this energy lines, this band structure, it shows which energy can get our electron in this system. So this is allowed energies. But for example, in the system, electron can't get this energy or this energy. It can have energy only on these lines. It goes from, as you see, it goes from quantum, from some quantum from quantum nature, because the difference between center of Brillouin zone and border of Brillouin zone, it goes from Heisenberg principle, from this distance, then and from distance between atoms, and this and energy value, it goes from a combination of these states. Now we can try to calculate this band structure, but for our 3D system, for diamond silicon. You can see this algorithm, 0.0 step convergence test and relaxation. I haven't told you about relaxation yet, but it will be the topic of our next laboratory work. So we have provided convergence test, and it is enough. In most cases, it is enough convergence test. So that's why last time we made this convergence test to use in today's calculation good set of parameters which we have estimated by convergence test. Step 1, self-consistent calculation. Self-consistent calculation is the most crucial part of this algorithm, because all our algorithms for calculating a lot of properties will be start from self-consistent calculation, because we should get wave functions from some calculation, and self-consistent calculation is great tool to achieve some wave functions. We should get energies, we should get crystal structure, and all these tasks we made by this simple self-consistent calculation. Then we'll provide non-self-consistent calculation. I will explain you what is it, what is non-self-consistent calculation, and also I call it band structure calculation. So it's the same, band structure or non-self-consistent calculation, and we will make this calculation along high-symmetry path in Brillouin zone. And so we will choose all these letters, gamma, X, M, and some other letters in this Brillouin zone. And we have post-processing. It involves, we will extract energies from output and make some tricks with them to plot them with Python. Last years, we used GNU-plot, and it's in most cases, it's simpler. So in most cases, GNU-plot's scripts simpler than in Python. But I think that we can, that if some of you are going to machine learning course by Tim Chishan and Bezguba, and this course is on Python, and this will be good for you to use Python also here. Okay, first step, self-consistent field calculation. And we have seen all these parameters. We have seen this input last time and on previous time, so also on previous lectures. But what I have changed here, I used CLDM, which we estimated in convergence test. Last time we made this parabola, and we saw that we saw the center of this parabola was 10.2. So this is the best CODM parameter for silicon. Then we have chosen ECAT WFC, ECAT energy. So we also estimated it. And we also estimated key points. It was 12, 12, 12. So for this, our first self-consistent file was like 18. ECAT WFC, it was 18. It's almost nothing. So it's not good energy cutoff. And it was 888 key points, which is also not great, not great grid, not great, but not terrible. So, and we have these three parameters. This is new parameters in the self-consistent file: occupations, smearing, and degauss. What is occupations? For example, you have this energy structure. This energy structure, band structure for silicon. It was created by some guys, but we will get something like this. And you see that this line it is just a line, and it has one electron. So on all these lines located valence electrons of the system. So we have for silicon we have four valence electrons. So 4 electrons which can be used for creating some bonds, and that's why on each of these lines will be 1 electron from one silicon and 1 electron from another silicon. So it will be two electrons on each of these energy bonds. Here, and here. And here will be nothing, because we are working at 0 Kelvin temperature. So these bands, conductive bands, will be this part of plot is called conductive bands, and here are valence bands. I think that you know this. On conducting bands we will have nothing. On valence bands we have some electrons. But if we will calculate some metal, in metal we will in semiconductor it is simple. These bands are filled, these bands are empty. But in metal we will have some bands which goes from above Fermi energy, and then it goes below Fermi energy, and we don't know its population. So what is population of a band which behaves in such way? We don't know. That's why we should make some. That's why we should take here not 1 electron, but some electrons between 0 and 1. And with this task works occupations. So by choosing occupations, I tell the program that it should take not 1 or 2 electrons on these bands, but it should take some number of electrons from 0 to 1, because we don't know how many electrons here. And it also makes some another way, some another important thing. Maybe you remember from Monday's lecture how ARPA spectrum looks like. So they are rather wide. We don't have what is wideness of this line? 0. We don't know. We can say, I can say how long it is, but I don't. I can say how wide it is. How wide is this line? By setting these parameters, I can smear this this line, and this line will have some wideness, because electrons, they're not located on this ideal line with zero wideness. It will be smeared on this line. So by using these parameters, we are making our system more real. And also, it is crucial, for example, for semiconductors or insulators, we can use default occupations. Default occupations, they just take one electron here, and the 0 electrons here, and it will be okay. But for metals, we should use some occupations. And here I use the simplest occupation, Smearing occupation. And then from the Smearing occupation, I choose Gaussian smearing. What is it? I calculate this electron density by this way. I calculate it's some squared, psi squared, wave function squared, multiplied on some band occupancy. So on how much electrons on some band, and we can for very simple case we have only phi is can be 0 or it can be 1, like in that one chain example, 0 or 1. But if I add occupation smearing, I make this this occupation not so simple, and I set them by this Gaussian function. So I tell the program that our occupation will not be binary 0 and 1, but it will be something between 0 and 1 with this formula, with some Gaussian formula, and the Gauss parameter 0.02 is this sigma parameter. So by the Gauss, we tell the program how to smear this band. And for insulators, it should be rather small. So it should be smaller than our gap, because if the Gauss will be very huge, for example, here we have gap like 0.4 electron volts. If I will set here 0.5, so it will overlap. So it will overlap this gap, and we'll have some crazy results. So for insulators, it should be rather small. For metals, it can be higher. So for metals, we can choose 0.2, 0.5, 0.4, and even more, because it's metals. Because we don't know what happens. We don't know exactly what happens there in the metal. But for insulators or semiconductors, we more or less know it. So it's what about the Gauss? I will show. It's what about occupations. I will show you it in. I will show you it in Quantum Espresso site. Occupations. The Gauss. Here, occupations. What options do we have? We can use smearing and use Gaussian smearing. It is best. It works. It is a very good option for metals, as I told you. But for insulators or semiconductors, you should use a very small degauss parameter. Then we have 3 tetrahedra. We will use it. It's also very useful occupation. So it's the way of integrating Brillouin zone, and I will tell you about it on one of next laboratories when we will calculate density of states. Because these tetrahedra occupations, we can calculate density of states only using tetrahedra occupations, not with smearing, with fixed. Fixed is very simple, and it stays by default. Only for insulators with a gap. What makes this fixed occupations? They just call that here, on all these bands will be 1 electron. It's very simple. it's great for semiconductors, but not great for metals, because for metals we will not get Fermi energy. We will get okay, for metals the calculation will not even start if you will use fixed occupations. Smearing is good choice for most systems. And what about smearing? Here we have some ways to smear these electrons on this band structure. Gaussian, Mansfeld-Paxton. It calls for the names of the guys who made this scheme. Mazary-Vanderbilt and Fermi-Dirac smearing. For example, I used here very good. I made some link to a very good site here, which explains how this mathematic works. So how it works for every for Fermi-Dirac, for Mansfeld-Paxton, and some other. For example, for Fermi-Dirac, we just use this function. We just use Fermi-Dirac function. And here, the Gauss, it will be temperature broadening of this thing. For very, very good calculations, we also had to converge this parameter, this degauss parameter. So it's another parameter we had to converge, but for our calculations, I think that we shouldn't do it, because accuracy of our calculations not so good, and we can use it just rather small, rather adequately small for insulators, and higher for like 0.2 for metals, and it will be great. Because you see energy difference, is not so huge, and here is for very, very huge grid, 35, 35, 35. So it's really dense. It's really dense key point grids. And here you can see all these plots comparing of these methods, and you can see some mathematics which stays for each of them. For example, Mansfeld-Paxton. Here's mathematics behind this occupancy level. It's mathematics which stays behind all these options, all the smearing options. We will use the simplest Gaussian, and I think that it's great in most cases. For our cases, for our education cases, it will be very good. So the smearing, occupation smearing Gaussian, and the Gauss I choose not so huge because we are working with insulator. And another new parameter, nbnd. Maybe you can guess what it means. It's number of bands. Yes, number of bands. How can I choose it? I can choose it by knowing the number of valence electrons. For example, for our silicon, we have 4 valence electrons, and we have two silicon atoms in unit cell. So all our unit cell has 8 valence electrons. If I will use it by default, by default, it will be the number of valence electrons. By default, it will be half of valence electrons for insulators. So it will be like 4 by default. And but if I will use number of bands 4, I will get only these lines. I will get only valence bands, and I will not know what happens there. As I remember last time, maybe you, Alexey, asked me about this, about how to calculate these empty states. Yeah, so this is how we choose this parameter. If we choose it 4, it will be 4 only valence. If we choose it more, we can calculate. we can get these valence states. So for insulator, for semiconductors, it is half the number of electrons. Because all the electrons will be sitting here by two electrons on the line, two electrons by Fermi principle on this line. All electrons will be here, and we will get all valence, all occupied bands. If I will choose higher number, 8, twice, I can get 4 more bands. I can choose it like 20. So I will get 4 occupied levels, and I will get 16 not occupied levels, 16 empty levels. So because it is half the number of electrons. For metals, slightly more than half. So why? How do you think? Why should we take? Okay, for semiconductors and insulators, half the number of valence electrons will be enough. But why for metals we should take more? We work at 0 temperature. No such parameter as temperature. We can add temperature, but it's really hard. Yeah, for metals we have no gap, and we have some bands which goes from above Fermi level to below Fermi level, and we should. And if we will choose only 0, if we will choose only half number of bands, like for semiconductors, we'll have some filled bands, and we'll have some parts of bands. So we don't know. We will get some part of bands we will here, but we don't see here. Like in Shining by Stephen King, this portrait of Jack Torrance, which goes from the door. And you don't see him fully. You only see his face. So our creation will not even start if you will choose not enough bands. But here I took number of bands equal to the number of valence electrons because I want to get here 4 bands and here also 4 bands, because then we will have a great picture. Okay, we can make this calculation. We can make this SCF calculation together. We should go to lab 3, first folder, SCF. Here is my file. And I will launch this calculation. It will take few seconds, or even less. You can find somewhere shortcuts. You mean zoom in this file? I will cut all this from the file from YouTube. Last time I cut it 15 minutes. Okay, I have finished this calculation. I have we can compare. For example, you see SCF out, and what I'm interested in. You see this part K 0, 0, 0. It's the center of our Brillouin zone, gamma point. And then you see 8 numbers, 1, 2, 3, 7, 8 bands. So each this number corresponds to some energy band. Now I will just open some file from our first laboratory work. This is first laboratory work where I used n bands by default. By default, it uses half of valence electrons, so it was 4. And I expect to see here 4 numbers, and you see 4 numbers. So if I will use n bands by default, I will not get all the conduction bands. I will stay here. But for our situation, all is okay. Then I had to copy. What is okay? I should copy all of this. You can see if the self-consistent calculation was finished successfully. So this run was terminated, job done. You should see all this. 51 seconds. Wow. Okay, you should copy all these files to band folder. Yes, to band folder. Why should we do it? Okay, in out maybe we shouldn't copy, but I just copy all of them. What we really need, we need this silicon XML. It's a very important file. Without this silicon XML, we can't start our next part of calculation because it contains some information about our previous calculation. And out, this file out, SCF out, is only for us, for people. But XML is for the program. And we have silicon save. Last time I told you that it's a folder with all wave functions. You see, we have 72 wave functions. Each wave function was calculated in some irreducible key point. We have 12 multiplied by 12. I will calculate it. So 100728. 1728 28 key points, but all this huge number of key points only goes to 72 key points, to 72 irreducible key points because of symmetry. Yes. So each this wave function was calculated in some irreducible key point. And we need it as input to our next part of calculation. Band structure calculation along high symmetry. Here you see some new things. This type of calculation is called non-self-consistent calculation. Before we used self-consistent calculation. What does it mean? It meant that in Kohn-Sham scheme, you change electronic density, you change then kinetic energy, you change energy, you change electron Hartree interactions or Hartree energy, and some other things. But by non-self-consistent calculation, you just take electron density from self-consistent calculation, from previous calculation, and use this scheme from non-self-consistent calculation, but with not adjusting your system to your electron density. So it's just like some additional step to self-consistent field, but non-self-consistent field. So our electron density will not consist with all the system, like in self-consistent, like in self-consistent calculation. It calls non-self-consistent calculation. And by this non-self-consistent calculation, because we have pre-calculated electron density, so we shouldn't calculate electron density. We use this scheme, but we don't change electron density. We use it from self-consistent calculation. That's why we can use some tricky points as another key points. Last time in self-consistent calculations, we used this 12, 12, 12. So we just took our beautiful Brillouin zone, divided it by this points on some. So we cut it with points. Then in all points we have calculated energy, electron wave functions, and so on. Electron density we have calculated, and we need this key points grid to calculate electron density. But if we already have electron density, because we have calculated it from SCF calculation, we can choose some interesting path in this Brillouin zone. We don't need all these key points, but we can choose from these key points only interesting for us. And we will do it by this input. So by this input, I choose the line in a Brillouin zone, which I want to in which I want to make these calculations. This line will look like this. So I start from key points crystal B. It means here it was, you see, here it was, okay, it had to be crystal here. I will change it, not to make this. It had to be crystal here. What means crystal? A crystal means that all these coordinates is some part of lattice vectors. So this coordinate is 1/4 from A vector, this is 1/4 from B vector, and so on. It means crystal. But if I will use crystal B, it means that we have gone to reciprocal space here. It is the same, but in reciprocal space. Here was real space from A, B, C, and here we see B1, B2, and B3. And these coordinates will be some this coordinates 0.5. It means that it's half of B1 vector. This 0.5 means it's half of B2 vector, half of B3 vector. So it indicates that we are working in reciprocal space. It's very important to notice crystal B. Then 5, it means that we use 5 key points. I will explain you slightly later how we choose these key points. And now L here. Then gamma, we are going from L to gamma. Where is gamma? Here L, and we are going to gamma. Then we are going to X here. X is the middle of plane of this plane. The middle of this plane. In 2D case, it was middle of some line, because this line, the line was here. Because this line was some side thing of this square. It was the middle of line. But in 3D, it will be the middle of the plane. X, then U here, and gamma to doom, and we from U to gamma. So we have made some closed path. We choose from L to gamma, then to X, then to U. Okay, maybe it's not ideal example, because this example was for this picture. So L, gamma, X, U, and then they also go to gamma. Okay. How we can choose them? We can choose them by some very useful thing. Cause okay, we have these two sides. One of them is called Bilbao crystallographic server. It's very useful thing. Bilbao crystallographic server. Or maybe I can send you this link into Telegram. If I will Google it, I will get this starting page. Then I should use space group symmetry. Then I should use then I should choose K vector, the K vector types and Brillouin zones of space groups, K vector. And then I should choose our space group. I don't remember our space group. It is 229 something. I can materials project. I can see it in materials project. Here is cubic C. And here is 227, our space group. So I can type space group here in Brillouin zone 227. And I will have all information about Brillouin zone, which looks crazy, absolutely crazy. Here is Brillouin zone of our cubic silicon. So L, gamma, high symmetry points, which means that you when you apply symmetry, these points don't not change. Only gamma, L, X, M, W, V, and this Greek letters like lambda, delta, it shows some side points like this. So it's not so important. We will work with only these capital letters, X, L, gamma, and so on. And we should choose some close path inside this Brillouin zone. And here you see some useful information. You see coordinates of these points in Brillouin zone. Gamma 0, 0, 0 because it's center. X 1 half, 1 half, 1 half, and we can see them here. 0, 0, 0, 1 half, 0, 1 half, 0, 1 half, 1 half, 1 half, L. Where is L? Here is L. So we can take coordinates from here, from Bilbao, by choosing space group, and Brillouin zone corresponds to some space group. And how we can see the path? We can our goal is to choosing the path is some kind of magic, because you don't have some we don't have some algorithm which we had to follow and we can choose this path. We can choose this path according to our task. If we want to see the energies in the whole Brillouin zone, we should take as long path as we can. And in more cases, just rather just not so short path, but closed path is okay. And we have another usable tool which calls SCF-pass. I will show you how it works. Last time I have shown you SCF-pass. SCF-pass, and I open it in my virtual machine. Okay, save in. Here is our structure, and here is our Brillouin zone. And here you see all these letters. Gamma in the center, X in the center of this plane. K is the center of this side line, and L is the center of this. Okay, X is the center of the square plane, and L is the center of this hexagonal plane. U is the center of this side line. And what it suggests? It suggests this path: gamma X U gamma L W X. You can take the coordinates from it. There is no such thing as the better pass or worse pass. You can choose it as you want. If we have some okay, we think that we need to have as much information about a Brillouin zone as we can. So that's why we should take as long path as we can. And it can be some closed path. Why? Because if we will use some closed path, for example, you can see it here. You can go to some gamma. We have this point gamma. Gamma is very important point in all Brillouin zones. So if you will choose some path where you can you have few gammas, for example, here gamma and here gamma, you can see how this energy changes from approaching to this gamma from the L point, from approaching to gamma from X point, from approaching to gamma to X point from other side, and so on, from K point, from U and K point, and so on. So it's interesting to see the bands here. And in Monday, Alexander have showed you RPS, and RPS is very, very, very tiny part of this plot. So this plot is like a world map, and RPS is a map of your own district. It's some Sputnik photos from some small region, and this is huge world map. And you have to get as much information as you can. So for example, this picture I took from some scientific paper, and I think that their path is rather good. So L, gamma, X, then U here, U, and then gamma. And that's why I choose L, gamma, X, U, gamma, despite that SCF-pass have suggested this path. But it's always the same. Gamma X, U, gamma L. I just took L not in the end, but I moved L to the beginning. So we have so it's the same. It's just this part of path. And I usually take key point coordinates from Bilbao, but it's some, so you can take it from here. So gamma 0, 0, 0. L 0, 0, 5, 0, 5, 0, 5. Here is L. Then gamma 0, 0, 0. Then what is then x 0, 5, 0, 0, 5. I can also see it. X 0, 5, 0, 0, 5. Then I go to U. U has this crazy coordinates. And then I go to gamma to zeros. And all these coordinates I have put it here. And I'll get this picture. So why I choose it? Because I want to compare with something. And I want to compare with some literature data. It's the best way to compare, to have the same, to take the same path. And we can start it. And you should, okay, PWX psi band in, silicon band out is our band calculation. And we got psi band out. We can, but from this file we can get not so many information. It's just some technical information about the calculation. For example, key points, all these irreducible key points, 81. You see 81 key points. Why we have 81 key points? Because we have where is psi band? Because okay, I didn't tell you about this number. It's the number of key points between these dots. From this L, I go. Okay. In the line from L to gamma, I have 20 key points. There I have 20 key points from in the line from gamma to X, 20 from gamma from X to U, and 20 from U to 0. And here I can type just what I want, plus 1 point, and plus 1 point, so 81.
So what are the points on the graph? Yeah.
Yes, we will have 81 points on the graph. We can choose 100, for example, here, and or 1000 if you want to take some tiny moment in our band structure. We can make very good resolution, but for this calculation 20 is okay, even more than okay. So that's why here you have this 81 key points, because this is our line. What another information I have, and also I have this information. This is very important for us. Band energy. And we had band energy from SCF calculations, SCF out. Yeah, I will compare. But it was just band energy for some key points. For some key points from this automatic grid. But here we have this energy for our path. For path we want. Here we also start from here we start from 0, but then we go to some you see 0.0833 and so on. But here we have our path 0.5, 0.5, and then we go, and you see that we are going from there or here gamma point, yeah. Okay, but we still can't work with all this data because we should extract it. We should extract all these energies in some adequate, convenient form from this file, from file C-band out. And for this purpose, we use this file, C-band2 in. Here is it, post-processing. This simple file, this simple short file, here you see bands. Here it was some control system. Here you see bands, prefix silicon, audir, prefix just the name of folder, audir where all results are, and fill band means name of file which it will create, and that's all. It's very, very simple. We should just start this file by this command. Command bands.x, not pw.x, but bands.x. Then C band 2 in, C band 2 out. Usually it is very fast. And I have few files. I have a few formats. C-band that. You see, it just removed key points and this energy, but it's also not so convenient. And bands 8 NKS number of Kohn-Sham states 81. C-band that GNU. This is file we want to use. You see, it's just two columns. It's just two columns of data, and we can easily plot it with this simple script. I will show you the script. Just I took the script and slightly changed it from Quantum Espresso Git directory. So here we import matplotlib to make these plots and import numpy, and that's all. So it's very simple. Here is some parameters of the picture, DPI, color, figure size. Then we load data. So this file C-band that GNU on this simple file data. Then I choose key coordinates in key space from this file. Then I choose, so I will show you it again. Okay, this first column is coordinate in key space. Second column is energy. How we can calculate this coordinate? Our task is to take this 3D path and make from this 3D path 2D path to make this plot. That's why I just take this first letter 0.5, 0.5, 0.5. I tell that this is our start of our new. This is the start of our new plot 0.0. Then I calculate by Pythagorean theorem the distance to gamma point. It will be just root square from 0.5 squares multiplies 3. I take coordinate of gamma point, and then I divide it by 20 because I have 20 points between them. What is so here is L point. Somewhere I will see a gamma point. I think it will be here. This will be our gamma point, and so on. I hope you understand this. So I take first column as coordinate in key space. It will be our coordinate x in the plot, and here will be our coordinate. Here will be our coordinate y bands, band energy. For each k, I have 8 bands. I also will demonstrate it. Here, for 0, I have minus 3.4914. Then I move to another band. You see, we have also 0. 0, it will be minus 0.86. Then I move further 0.50074, and so on. And I will have this 8 energies, which will be corresponds to 1 0 key point. And that's all. So I just choose this. I make some bands. So here will be n bands. So it will be 8 bands. Yeah, here, which will correspond to each k. Then I take Fermi energy. It's very important thing. And where you can take it? You can take it from SCF calculation. CSF out. You take Fermi energy from here. The Fermi energy is 6.4346. I should type it here in my script. 4346 Fermi energy, and then I just plot it, and that's all. So all these parameters, it's for plot the bands. Here we plot each band. Here we plot all these supporting lines, this line, Fermi energy line, and so on. I hope that after maybe after our laboratory work, you will work slightly with this file, and you get familiar with it. From SF. In band calculations, we don't have Fermi energy because we use it from SF calculation. It's also the data which we use in band structure calculations. So this coordinate will be 0 for L. For gamma, it will be 0.86. For X, it will be 1.69. You should take it from band out, C band to L out. You will see this thing, and it will take you coordinate of key points in this on this 2D plot. So distance you can create it. By Pythagorean theorem. So distance between this and this, it will be exactly 0.68. Distance between this and this will be 1. So 1. Between this and this, it will be this minus this, and so on. And you can take this coordinates to your file. Here, C bends to out, and here you see these coordinates. They are already typed in this plot. I just explain you why I choose these numbers, just to type these things. And as I remember, you had to install matplotlib. It's like pip install matplotlib. I have it, but you had to do it because it is not installed by default. pip install matplotlib, and then you use Python 3.7 and this script. Ta-da! We have our plot. Tell me if you have some problems. Not like existential problems, but with this plot.
Can you please show the script one more?
Yeah, 1 minute. You should change here. You should make this 43, 46. Here I see all these lines, gamma, L, gamma, X, U, gamma. I see these Kohn-Sham states or these bands. So 1, 2, 3, 4. You see these bands are degenerated. We can say that these two bands in the path from L to gamma and from gamma to X are degenerated because they are the same. You see, these lines are the same, but then they go by different ways. You can calculate, you can estimate band gap from it. You can see that here calculate minus 0.21, and here something like 0.29 and 0.21. Yeah, we have 0.42 electron volts band gap, and what tells us materials project 0.61 for their input. So for their input, but they have used another pseudo potential. About pseudo potentials, we will have standalone lecture, and then we will use better pseudo potential, because here we used only the most simple LDA, local density approximation pseudo potential.
Could you please show how do we approximate
Band gap? By the yeah. So this and this. Of course, you can calculate it. You can take the file. You see, you can find the highest energy. You can find the lowest energy. Of course, for paper, it's not appropriate way to say that this is. And some other guy, some referee will say, okay, but I see here not 0.25 but 0.30, and it will be the same thing. But of course, for paper, we should take the file, should find the highest energy, the lowest energy, and then create it. But for very root estimation, it's okay to use this way. And I had seen hundreds times when some scientists made estimations by the eye. So your eye is a rather good instrument for this. And if one will create some ARPA spectrum of this silicon, I think that it's impossible because it's semiconductor. But okay, if somebody can see ARPAs from this material, he will see only this tiny part. Right bottom here. Yeah. You mean coordinates like here, yeah? Just X is just Y coordinate. I don't see X coordinate, but I see only Y coordinate. And Y is energy, so it's like.
So,
Hmm? Of course. You mean that we can?
You can zoom to.
You mean that we can zoom? Yeah, I can zoom it. You see, 0.16. Yeah, 0.16, and then 0.20. We have the same 42. But never mind. You can find this file, see bent out, and you can find the energy. For the calculation, we used LDA, pseudo potential, low density approximation. It is very simple pseudo potential, and then we will use more advanced pseudo potentials, and you will see that results will be changed. But real experimental band gap is 1.1 electron volts. So it's not 0.30 something, and it's not like 0.61 from materials project, because in materials project you see only the information from some calculations. So their calculations get them 0.61. And it's a problem for DFT, for these methods that we use, for these pseudo potentials, to get exact band gap. And on one of next lectures, I will tell you why it is so hard. And I will show you then some hybrid functionals which deal with this problem. Yeah. So for insulators, it underestimate. DFT usually underestimates band gap. So it's like not 1.1 experimental, but 0.45, 0.61, and so on. And for very tiny band gaps, like 0.1, you should be very accurate, because it can show you that it's a metal. So that 0.1 experiment, for example, experimental can be 0.1 electron volt band gap, but DFT will show you that this material is metal, because it underestimates it, because its accuracy is not enough to take this 0.1 electron volt with these pseudo potentials. But for other pseudo potentials, you can do it, because people can solve this problem. But you need to spend much more researches to get accurate band gap. For metals, DFT works well. Why? Because DFT was born from Thomas Fermi approximation, and Thomas Fermi approximation was for ideal electronic gas. And ideal electronic gas works well for metals, not for insulators or semiconductors. That's why we have some problems with these materials. But it's rather good, but it's also rather good. 0.61, it's a rather good estimation. Better than nothing. So for now, I think it's all.